All right, gang, Math 5500. Got a lot to write in this video, and I find that if I write during the while I'm presenting the lecture, creating the instructional video, that my writing isn't as good. Um, so you may look at this and say, well, it's not really good when you pre-write it either. But anyway, taking a little different approach and just I already have the presentation written out, so I just want to go over this with you. All right, we are in the simple, and over on the right, you'll see that I have some things I've already done with R to demonstrate a couple of things. So anyway, if I sound a little bit frustrated, it's because I am. I just got off the phone over an hour with, well, I'm not going to name the company because I may get sued, but we canceled our DSL service because it was horrible. And canceled it over a month ago. They canceled the service because the modem went red, but they didn't cancel the bill. Now they're telling me, oh, okay, anyway, it's just, if I talk about it too much, I'll get more frustrated. So hopefully teaching stats will bring some joy to my day. All right, gang, we're in simple linear regression, and that means that we have one predictor. And we're looking at the ANOVA approach, which brings to the table a little different approach to testing whether or not we have statistical significance uh, of our slope, beta 1. So the null is that beta 1 is equal to 0, assuming that we have no linear relationship. The alternative is beta 1 not equal to 0. And our test statistic, well, assuming that we have a linear relationship. And so in other words, if the evidence supports H sub O, we fail to reject. Our test statistic is greater than our p-value. Then we assume no linear relationship. And if our test result is more supportive of H sub A, meaning that our p-value is less than 0.05, then we can assume a linear relationship. For the ANOVA model, our test statistic is F star, the mean square regression over the mean square error. We've talked about that in a previous video, so I'm not going to beat a dead horse. And the result of this, if we have a large value of F, we will get a low p-value, which is evidence in support of H sub A. Contrary to that, if we get a small value of F star, that will give us a high p-value, which provides more evidence in support of the null hypothesis. Now, we've seen before, I think this is kind of cool stuff, this part right here. Not, this is cool too, all right, but this is kind of cool too. We've seen previously that if we run our model that using a t-test, using the LM function with R, and compare it to the f-test with the ANOVA, that the t squared is the same as the f. Now, I have this over here. I'm using the ACT data set, and I just ran the model. And for the estimate for beta 1, we can see that our t-value is 10.41. And when we do the ANOVA, we can see that our f value is 108.47. Well, you can test me out on this. If you take 10.41 and square it, you get the f value for the ANOVA. So they're kind of saying the same thing. So, we also saw previously that the sum of squares regression, well, this is an interestingly, because this was just a given, really, that we calculate the sum of squares regression by looking at the difference between the predicted and the means and square those and sum them up, just as we've seen previously. What I think is interesting is that the sum of squares regression can also be rewritten like this. Now, the proof is a little lengthy. I'm not going to demonstrate it. I don't even know if I don't know yet whether that'll be a homework assignment problem or not. We'll see. But anyway, you kind of want to pump the brakes here and realize that the sum of squares regression calculation here is using the mean of the y's and the predicted, so it's using the regression model. Whereas here, it still uses the regression model because it's using the B1, the estimate of beta 1, but it's looking at the differences in the deviations in the x. So anyway, just a different presentation. Now that comes in really handy when we prove that f star is actually equal to t star squared. So if we look at f star, it's a sum of squares, well, it's the mean square regression over the mean square error. And now knowing that we can rewrite the sum of squares regression using this form, we have that form divided by the mean square error. But guys, previously we've seen that the variance of beta 1 is equal to the mean square divided by the sum of the deviations squared for x. Or we can see equivalently that, just flip those, giving us that f star is beta 1 squared. Again, it's all that's left up here after flipping to get this form over the variance of b1. Look at that quantity squared. And of course this value in here is just t star. So resulting in the following, again, important to remember that the t-test is a two-tailed test and the f ANOVA is a one-tailed test. So a little bit of this is just review and just rehashing some things that we already know. Going to move into now descriptive measures of linear association. This was a tough thing for me to teach. Not that it's difficult, but the tough part was how in depth do I get? Because I could turn a large portion of this class into just looking at descriptive measures of linear association. But I think we have bigger fish to fry, so I've condensed this down to cover the bare bone basics, if you will. So the first thing I want to look at is the coefficient of determination. And recall that the sum of squares total looks at the deviation in y's but doesn't consider the x's. The sum of squares error looks at the deviation or the uncertainty of, I should say, predicting the y's using the x's. So what we can look at r squared is it's 1 minus the ratio of these two, 1 using x, 1 not using x. And with just a little simple math, well, actually arithmetic, we can see that this is equivalent to the sum of squares regression over the sum of squares total. Now, if I'm going to calculate r squared by hand, then this is the form that I'll always try to get the result in. And just make here a note that r squared is usually reported as a percentage, and what it expresses is the percentage of variation in y that is explained by the regression on x. So if we go over here, we can see that from the ANOVA model that the sum of squares for the regression is 15.16. This output doesn't give the total sum of squares, but we know that it's just 15.16 plus 98.25. So this situation, it looks like, let me put that in the calculator real quickly. Looks like 13.4%. So we can say that 13.4% of the variation in first year college GPA, or I'm sorry, first year college GPA. See, we're taking ACT. I got this backwards. We don't want to predict ACT We want to predict first-year college GPA. So I've just completely messed this up. So let me correct that. So we want to, let's just do a model new because Dr. Darbro screwed the other one up, got in a hurry. So we want to predict first-year college GPA from ACT. Would tell you that's the first mistake I've ever made, but I don't think you're buying that by now. Okay, that makes much more sense because the ACT would be taken before your first year college GPA in most cases. So what we have here is I can do my ANOVA of my model new, and so we get our R squared. No, I better not do that. I don't think that R would handle that right. Would just be the 37.889 divided by 37.889 plus the sum of squares error. A lot of error in this model. So still 13.4%, which makes complete and total sense, right? So we would say the 13.4% of the variation in our Y, which is first year GPA, would be explained by the regression on ACT. Right. Had it right over here. For some reason, I got over here and did it wrong. Interesting stuff. All right, but it happens. All right, at least we got it corrected. Now, moving on. I actually had some feedback from students and creating videos. And two things that my students, when we did our pilot group, and we did. We still do student evaluations, but we did more in depth. We did some interviews and what are we doing wrong, what are we doing right. How can we improve our program? And one of the first things we got from our pilot cohort back in 2012, and the other one in 2014, is we need to move fully online. At that time, we had 5 on-campus visits, different places around Ohio to meet the locations that were convenient to our cohort. But anyway. But another thing they said that I thought was very interesting is we like it when you make a mistake or something happens when you're posting a video. And I'm like, what? And they said, well, like the dog barks or the UPS person shows up or the FedEx, shows up. It makes it interesting. I found that really interesting. So if making an error makes my instructional videos more interesting, then this video just really got interesting because I magically switched to my independent and dependent variable. All right, and there we go. On command, my daughter gets ice, and so there you go. I don't know if you could hear that or not. R squared, proceed with caution. And this is something that I get a lot. So let's just cover 3 things that you need to have on your radar. First of all, in isolation of other information, a lot of people think that if R squared is high, then it indicates that we have a good fit, good model fit. Well, that is not true. Second thing, we very similarly, we think if we have a high R squared, it indicates more accurate predictions. That's also not true, especially as we deviate more from the mean of the x's as we get further in the tails of the predictive model. And the third thing is a low R squared indicates X and Y are not related. Now, I want to talk about the first one. What I did is I just created a data set up here. I just called them X and Y. All right, so plug that in. You can see the correlation is 0.87, and that the R squared is 76.2%. So 76.2% of the variation in Y is explained by small changes in X or the regression on X. But if I do plot xy, and again, in isolation of anything else, an r squared of 76.2 indicates a good model fit, right? Well, no, it doesn't. Because if we look at the plot, you can see that we have a curved nature right here, and a linear model is not appropriate for describing the relationship between x and y, even though we have an r squared that is relatively high, pretty close to the threshold of 80%. So, proceed with caution there. Another thing, number 3, a low r squared indicates x and y are not related. A low r squared indicates that x and y are not linearly related. We can explore relationships between x and y with other types of models. Quadratic model, if we have like a U-shaped scatter plot. It doesn't mean that x and y aren't related. They are related. They're just not related in a way where a linear model is appropriate for describing that relationship. All right, enough about that. Moving into a correlation coefficient r, it's just the square root of r squared. Well, it's the principal square root, so your answer will always be positive. You have to determine whether the plus or minus is appropriate simply by looking at the sign of B1. Again, B1 is the slope of our model. It makes sense that if we have a negative slope, then we would have a negative correlation. If we have a positive slope, we'd have a positive correlation. The inference process is to, hold on just a second. Hey, Bailey, will you take this phone call? It's about Kiki. Hurry up. And just get the information, and thank you. Our cat is in the vet. Well, this is just taking the distraction. Almost like it was on cue. So where was I? Okay, r squared. Okay, plus or minus based on B1. Okay, so the inference process is pretty much very similar to what we did for beta 1. We have a population parameter. In this case, it's rho. The MLE of rho is r, and r can be calculated like this. So the equivalent would be a population parameter being beta 1. We would have the MLE of beta 1 being B1 or beta 1 hat, and we would calculate it as we've seen in previous videos. All right, a little bit about R. R is a biased estimator of rho. Typically, we want unbiased estimators of rho, but when our sample size is large, it actually converges into being an unbiased estimator. Our R value will always be between -1 and +1. Really interesting proof using the relationship between the sum of squares regression and sum of squares total. May have that as a homework assignment. So anyway, the procedure is identifiable. It's something that is recognizable, I should say. H sub O, the rho is equal to 0, indicating no linear relationship. H sub A, the rho not equal to 0, then indicating we have a linear relationship. The test statistic is super easy to find. It's just the correlation coefficient times the square root of n minus 2 divided by the square root of the quantity 1 minus r squared. Follows a t-distribution, degrees of freedom, n minus 2. Now, important note, and again, I have to decide what to teach and what not to teach. We have bigger fish to fry than spending an entire unit on correlation. But please tattoo to the brain that when x and or y deviate from x and y deviate from a bivariate normal distribution, the Pearson product moment correlation, which is what I just demonstrated here, may not be appropriate. So you can get into some non-parametric stuff, even some correlation for if your variables are dichotomous, such as Kendall-Spearman. Kendall or Spearman, or something we call the point biserial correlation. So you can investigate those if you're interested. Now, one more reason I feel comfortable skipping in this course is I cover these in 6620, I believe, 6610 or 6620. Pretty sure it's 6620. So I believe that's it. Yeah. So, guys, sorry for the disruptions and interruptions, but just is what it is. Take care.